Gauss's law for electrical fields. What is Gauss's law all about? So Coulomb's law is essentially a mathematical representation of an experimental observation. So we define the electrical fields of a point charge Q0 such that E equals F over Q0. Starting from this, we generalize to infinitesimal assemblies of point charges and different charge distribution, for example in a line or a disk. Gauss's law provides us another way to calculate electrical fields. It is equivalent to the Coulomb's law for point charges. Anything that we have done so far could also have been done if we started with Gauss's law instead. So Gauss's law versus Coulomb's law. What is the advantage of one over the other? So Gauss's law is a simpler way to calculate electrical fields for cases with high degree of symmetry. In writing the Gauss law rather than the Coulomb's law for electrostatics, we can develop a system of equations for all electromagnetic phenomena that illustrate clearly the relationship between electric and magnetic fields. Gauss's law is valid for all charges, stationary or moving, whereas Coulomb's law is only valid for stationary charges, or charges moving very, very slowly. Coulomb's law can be derived from Gauss's law, hence it is more fundamental, and it is one of the four basic equations of electromagnetism, which are also called Maxwell's equations. So in order to talk about Gauss's law, we need to define flux, which is very important. Flux comes from the Latin word meaning to flow. Consider the flux of a vector field to be the measure of the flow of the field vectors through an imaginary fixed elements of surface in the field. Flux is the measure of the number of field lines passing through an area. So in order to understand it, let's talk about water, for example. Volume flow rate through a wire. So volume flow rate, dV over dt, of a fluid running through a wire will be given by the velocity times the area, right? Where area is the perpendicular area along the velocity vector. Or it could be V, a cosine of the angle when the rectangle is tilted by an angle phi. Okay? Now think about this as water, right? So this is how water will flow. Now phi, which is the flux, is going to be given by V dot A. Same thing when we talk about a flat surface in a uniform electric field. We will replace the velocity flow rate vector with electrical field vector to get the concept of electrical flux. So it's pretty much the same thing, but instead of V, we will now get E because we are talking about electrical fields. So the electrical flux through the surface is just going to be E times A. Or at an angle, it will be A cosine theta, so E A cosine of theta. Okay? So the flux will be just the dot product of E dot A. So it's basically a dot product, E A cosine of the angle. Where the cosine of the angle is going to be this angle here. So be very, very careful when defining what angle it is. So flux is 0 when the angle between them becomes 90 because the area is now lies plane parallel to the flow and nothing flows through the area. So there might be actually flow there, but we need to calculate the flow through the area. So here, look at this picture. So the flow is electrical field lines go this way. So they go through surface 3 and 2. But they don't necessarily go through surface 4, 1, 5, or 6. Why? Because the number of lines crossing through is exactly the same, right? It's not perpendicular to the surface. Another important thing that we need to remember when we talk about flux is source versus sink. So same thing when we were talking about positive charges, we usually call them sources, and negative charges, we usually call them sinks. So a positive source charge will be the field, a charge providing the field, and a sink will be the one that's actually absorbing the field. So in our case, it will be positive and negative charges. Right? Again, more mathematically, flux through a plane surface of area due to a uniform electrical field will depend on the angle to the field. Make sure that it's perpendicular to the normal to the field. So in order to understand it, let's talk through a problem. What is the flux through a sphere of radius r, which is 5 centimeters, that has a point charge minus 2 microcoulomb at its center? So in this case, what it's saying is we need to calculate the flux through a sphere. So imagine this is a sphere, and it has a negative charge, as far as I can tell, -2 microcoulombs in the center. And the sphere radius is 5 centimeters. R is 5 centimeters. Now, how do we calculate the flux lines? Well, first of all, we need to know that since this is minus, these are going to be, the electrical field lines that are going to be created are going to be inwards. Yes. And so this is basically a sink. It's not a source, it's a sink. So it's going to be absorbing the field. What else do we know? We know about flux, that this is equals to E dot A, right? So all of these lines, since it's in the center of the sphere, are actually pointing inwards, perpendicular to each of these points on a sphere. So I can take the dot away. I get EA, right? What is E? E is the electrical field caused by this charge presence. So that will be KQ over R squared. And what is the area? It is the area of a sphere that we know is given by 4 pi R squared. Okay? Once we have that done, R squared and R squared get canceled. I get KQ 4 pi. So flux is KQ 4 pi. The interesting thing to note about the flux is that there is no dependency on R. What does that tell me? That tells me actually that I could reuse this radius here, here, bigger, smaller, whatever, because the flux lines are going to remain exactly the same. So let's do this. So surface 1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 going through. Same thing I could do with surface 2 and surface 3. There's exactly the same number of lines. So flux is independent of the radius of the chosen sphere. That's very interesting. Now let's talk about what is Gauss's law. Well, Gauss's law comes after Mr. Gauss. He was one of the greatest mathematicians who ever lived, and he contributed and he did a lot of work with math and physics. Gauss's law makes it possible to find electrical fields easily in high symmetrical situations. What we do is we draw electrical lines around charges that leads us to Gauss's law. The idea is to draw a closed surface like a balloon around any charge distribution. Then some field lines will exit through the surface, and some will enter or re-enter. If we count those that leave as positive and those that enter as negative, then the net number of line leaving will give us the net number leaving will give us the measure of the net positive charge inside. Okay, so Gauss's law in a nutshell is the flux is equals to the Q enclosed over epsilon naught. That's all it says. So this result can be extended to any shaped surface with any number of point charges inside and outside the surface, as long as we evaluate the net flux through it. So, Gaussian surface. Step 1 in solving a Gauss's law problem is to create an imaginary surface that we will call Gaussian surface that encloses the charge. Whatever it looks like, we just have to come up with the best Gaussian surface possible. Gaussian surfaces are carefully chosen to exploit symmetries of any situation to simplify the calculation of the surface integral. The Gaussian surface is a closed 2D surface through which flux or electrical field lines are to be calculated, and it has the property that the normal component of the field is constant over the enclosed surface. For a Gaussian surface chosen in such a way, for every point on the surface component of this electric field along the normal vector is constant. Then E will also be constant, hence can be pulled out of integration. So for us, because we are in the algebra-based course, we will not be doing integration, but I thought it would be interesting for you to at least see how it's done. So there are different types of Gaussian surfaces. There is a pillbox, there are spherical surfaces, and then there are cylindrical surfaces. So pillbox is the surface most used to determine electrical field due to an infinite sheet of charge with uniform charge density or a slab of charge with some finite thickness. Spherical surfaces are used in cases where you have either a point charge or a uniformly distributed charge, a spherical shell of charge, or any other charge with a spherical symmetry. You can bunch those charges up together and put a spherical surface around it. Cylindrical surfaces are used to calculate electrical fields produced by any of the following, for example, a long straight wire with a uniform charge distribution, or any cylinder or a cylindrical shell with a uniform charge distribution inside it. So what are Gauss's law good for? Well, they are very good for finding electrical fields of infinitely long uniform charge wires, or charge within a large thin flat plane or a sheet of charge, or field around two parallel flat planes, electrical fields inside and outside of a long solid cylinder of charge, inside thin cylindrical cylinders of charge, or solid charge sphere. Okay? Without actually deriving them, I will want you to get introduced to all of these possible scenarios and all of the E fields that go around it. So a coaxial cylindrical Gaussian surface is used if you have an infinite line of charge like the one shown here, and the E field, once you do the integration and calculation, comes out to be lambda over 2 pi epsilon naught r, where you need to know that lambda is actually the line distribution, line charge distribution. So infinite sheet of charge, the cylindrical surface is used to find something like this. The Gaussian surface will look that way, and you can find E field accordingly. And that E field is going to be sigma over 2 epsilon naught, where sigma is the surface integral. So a spherical shell of charge. For uniformly charged sphere, we can summarize shell theorems for electrical fields. We don't need to worry about those here, but what we will do is, under electrostatic conditions, the electrical field inside a solid conducting sphere is always 0. Remember that. Outside the sphere, the electrical field drops off as 1 over r squared, as though all of the excess charge on the sphere was concentrated on its center. Very similar to like a point charge, like this. So if you remember Coulomb's law, the picture in Coulomb's law, it kind of looks like this exact same picture. Another very important aspect is a spherically symmetrical charge distribution. This is important because of the thing that we were talking about. So outside the sphere, your electrical field is the same as it would be for a charge Q that was concentrated inside it. So if you were to be outside this surface, all of the charge will contribute, and so hence you will have a volume density. But inside the sphere, what is very interesting to note is only the charge that's inside will matter. Anything outside does not matter for Gauss's law, right? So what you will do is you will have E equals E dot 4 pi r squared rho 4 over 3 pi r cubed over epsilon naught. That's going to be your electrical field. Uniform conducting sphere of any radius, what you will see is on the outside, E will be proportional to 1 over r squared, just like that of a point charge, but on the inside, because it's now talking about a uniformly conducting sphere, you will actually have E proportional to r. Gauss's law and conductors. Gauss's law can be used to deduce the properties of conductors carrying a net electric charge. An excess charge placed on an isolated conductor moves entirely to the outer surface of the conductor. None of the excess charge can be found within the body of the conductor. And this is very, very important. So the charge on the surface, so for example, if you have a conductor that's shaped like this, all the excess charge will come on the surface. If you have excess charge on here, this completely will be empty. Right? If you have empty space inside and there's a hole in it, there will be no charge. Think of like the Faraday's cage kind of idea. If there is actually a charge on the inside, then there will be charge on the inside and charge on the outside. If we were to put our Gaussian surface inside the conductor, what it will note is that there was no charge outside. There was no charge. It will show that there is no charge in it because there's no flux line coming through them. And if we were to place an a Gaussian surface here, what we'll say is that there is only one charge Q present here.